Hi, I'm Amy, and welcome to Element14 Presents. Oh, damn, it's gone too far. Hi, I'm Amy, and welcome to Element14 Presents.
Amazing hacks. Inspired designs. Each week, Element14 Presents brings you innovative projects using electronics, engineering, and more.
Hello, you lovely people. This thing is an ETC Ion. It's a console for controlling theatre lights, and it's absolutely brilliant. It's got a small, portable size, but yet it's powerful enough to control lights in many small, medium, and even large-sized theatres. It's got keyboard for entering information, it's got these encoders for entering position and colour information, and essentially, inside the box, it's a normal computer running ETC's EOS software, which is one of the most widely regarded and well-established lighting control software for theatre use. And I love it. The only problem with this ETC Ion is it's not mine. The Ion, although it's one of ETC's smaller consoles, and this is in fact the older version of the Ion, they've released a new one called the Ion XE, even that notwithstanding, this would still cost in the region of 5 figures. And I'm not a theatre lighting professional. I do this stuff for a hobby, for amateur theatre. I can't afford an ETC Ion. Luckily, you can run the ETC software on your own computer in a form called ETC Nomad, and that comes at a much more affordable price. Instead of paying for all this computer hardware, you're paying for this itty-bitty dongle. And unlike the Ion, this dongle is mine. So you might think, that's great, problem solved. Well, the problem pretty much is solved for the most part. But this Ion has plenty of niceties that my ETC Nomad setup doesn't have. I've already mentioned this keyboard. I've solved that by buying myself a customizable keyboard. And as for connecting up your lights themselves, ETC sell a little interface box called a gadget. I've got one of those as well. I can run the Nomad software on a laptop, and I can connect a couple of touchscreen monitors. And for the kind of shows I do, like pantomimes in village halls, it's a perfectly adequate solution. There's only one thing that I'm missing, and it's these encoders. You can make do without the encoders. You can enter all the data numerically on the keyboard or by using the touchscreen, but it's less quick. You've got to take your eyes off what's happening on the stage and actually look at the things you're pressing. Well, I'm a maker. Let's see if I can do something better than that. Luckily for me, ETC have released a project called LightHack, and it's some code that runs on an Arduino, and it talks to one of these ETC Ions or to my Nomad setup, and it lets you control various aspects of the desk. And so with that, you can build your own encoders. And in fact, ETC have a starter package which contains an Arduino, a couple of encoders, a couple of buttons, and a little LCD screen to start you off on the way. This is great, but you may be sensing a running theme here. There's just one small flaw. On the Ion, the information about what each encoder is controlling is displayed on this little LCD screen below the encoders, but it's also displayed along the bottom of the touchscreen monitor. You can change which page the encoders are on. You can change what they're doing, whether they're controlling colour or position or the size of the beam. So you can change it by pressing a key on this keyboard. You can change it by clicking a button in the interface. The problem is, ETC have not made which page the encoders are on available in the API. So if you're building your own LightHack project, you've got to create your own solution for which page the encoders are on, and it's totally separate from the one that's on the console screen. And if you change your page, the console doesn't update, and if you change the console's page, yours doesn't update. And that's annoying. What does ETC expect you to do in that situation? How do they recommend you add encoders to your Nomad setup? They actually have a product that can help you out. This is the ETC EOS programming wing. You can buy this and plug it into your own computer when you're using ETC Nomad, and it's got the keyboard, it's got the encoders, it's even got these little slider things. And it's brilliant. These encoders follow exactly what's on the screen when you change encoder pages on the console. There's just one downside. This thing still costs over £4,000, and I still can't afford that. By now, I've exhausted every solution that ETC has to offer. Before I give up, I'm going to have one last-ditch attempt. I'm going to connect this device to my computer, and I'm going to see if I can clone the functionality that these encoders offer by reverse engineering the USB protocol. Let's get to it! I'm going to be using two tools to investigate this device, USB Prober and Wireshark. USB Prober is part of Apple's developer tools, and it lists details of any connected USB devices. It's actually been discontinued, but we can still find it on Apple's site. If you use another platform, you could try a tool like USB View on Windows or LSUSB on Linux. To find it, go to Apple's developer downloads and search for IOUSB. We're going to extract the app directly from this download rather than run the installer. Open the folder that ends with log. Right-click and choose Show Package Contents. Copy the archive file. I'm just putting it on my desktop. Double-click that file to uncompress, and then find the USB Prober app within. Since this is an old app, it's not signed with an Apple Developer ID. The first time you run it, you have to right-click on it and choose Open, otherwise macOS will refuse to load it. I haven't plugged in the programming wing yet, and USB Prober is showing internal USB devices from my laptop. I'll plug in the wing and click Refresh. It turns out that the wing is made up of multiple USB devices, including an internal hub. What we're trying to achieve here is to get enough information that we can build a device which appears to be one of the bits of the programming wing. We need a bunch of identifiers and settings to program into our Teensy. Which of these USB devices should I be paying attention to? The first one is just a hub and I can ignore that. But what of the others? The first time I investigated this wing, I went through the process I'm about to show you multiple times, once for each device. When we load up Wireshark, you'll be able to see which device outputs some information when we move the encoders. But for brevity, I'll give you a spoiler. The encoders are part of ETC EOS playback control. At this point, we should know something about how a USB device works. Each device usually has a single configuration. The configuration has one or more interfaces, which are like different classes of behaviour that the device has. And each interface has one or more endpoints, usually one for input and one for output. Here's that information filled in for the EOS playback control. We have one configuration, then two interfaces, one that's a human interface device with two interrupt endpoints, and one that's vendor specific with two bulk endpoints. Note these endpoint addresses. In hex, the input endpoints have an 8 in the first half of the byte, and the output ones have 0. In the USB spec, we learn that bit 7 represents the endpoint direction, and the endpoint number itself is stored in bits 0 to 3. So our interrupt input is actually endpoint number 1. That'll be important later. There's a lot of information here that we'll need, such as the HID descriptor. We're going to have to copy this directly into our Teensy code. Let's save this whole report as a text file so we can refer to it later. Now for Wireshark. This is a packet sniffing program. People often use it to analyse network traffic, but it'll do USB too. There's one thing we need to do before we can run it on our Mac. Enter this command into the terminal. This brings the interface for monitoring USB traffic online. Now we can start Wireshark and tell it to capture the XHC20 interface. When we do, we see a whole lot of USB packets scrolling past. And you might be thinking, how are we going to make sense of those? We need to apply a filter to make it only show packets from the device we care about. Remember that USB Prober showed us the device address? We care about the device at address 18, so I'll add a filter for that. On a Mac, we have to use the USB.Darwin version of this field to filter on. That caught me out for a while. There's still a lot of packets, since I've tried using this programming wing while Wireshark has been running. But notice they're not coming in continuously anymore. The packets seem to be in pairs, a submitted packet followed by completed. All USB transfers are controlled by the host, which in this case is my laptop. The wing wants a transfer to be made when the user turns an encoder, so the computer must first send this interrupt request, which is the submitted packet. Then when the user turns the encoder on the wing presumably responds with the completed packet and the cycle repeats. Let's try it out. I'm right. When I turn the encoder, a completed packet comes in, and then the host immediately sends another submitted packet ready for the next event. If we look at this submitted packet, and then the completed one which follows it, we see that the top two lines of hex are the same. This is the packet header, and it's how the computer knows which packet is in reply to which. But there's another 4 rows of data in the response, and this is the bytes that the wing is sending when I perform the action of turning the encoder. Let's play Spot the Difference. On this packet, I turned the encoder number 1 clockwise a notch, and on this one, I turned encoder number 2 clockwise a notch. We see that there are 2 bytes different, Maybe this byte represents encoder 1 and this byte represents encoder 2. That's all I have to do with Wireshark. Make every action I want to replicate one at a time and copy down the packet for each one. I'll go and do that for the motion of all the 4 encoders, and then we'll get on with building some hardware. Now I'm going to connect some encoders up to a Teensy to give us something on which to run our reverse engineered code. In many ways, the hardware is the least important thing about this project. All the interesting stuff goes on inside the Teensy, and it's important that you use a Teensy for this. The Teensy has a pretty easy to understand and customize USB system, so unlike some other Arduinos, we can make it behave like a completely custom USB device. Before talking about the Teensy, let's talk about encoders. Encoders are simply a rotating knob that rotates endlessly. Unlike a potentiometer, it doesn't have a beginning and an end. And every time it rotates one notch, then it sends a signal, and you can tell whether the rotation is clockwise or anti-clockwise. This is a very cheap encoder. It came with one of the Arduino starter kits that I have. But I'm not going to be using that. I'm actually going to be using these. This is a set of 4 encoders that I salvaged from a Strand lighting desk, and they are lovely. They feel incredibly smooth, and they're already lined up 4 of them in a row, which is exactly what I need. Now, the downside of these is I've downloaded the datasheet, and they actually require a 5-volt power supply. And as such, they put out 5 volts on their data lines. This is a Teensy 3.6. The Teensy 3.6 doesn't actually accept 5 volts coming in on any of its pins. If you send 5 volts, then you'll actually fry the Teensy. Really, I should have been using a Teensy 3.5, which is 5 volts safe, but I haven't got one. I've got this 3.6. Now, I've tried this before. These encoders, although they're rated for 5 volts, you can actually give them 3.3 volts, and they do seem to still work. So that's what I'm going to be doing. I'm going to be powering these encoders with 3.3 volts so that we send the right voltage to the Teensy. As for the circuit, there's absolutely nothing complicated going on here. For each of these encoders, I'm going to connect up their power and ground, and I'm going to connect their 2 data lines to pins on the Teensy. It really doesn't matter. As long as you've got a digital input pin, then it doesn't matter which one you use. So let me just do that very, very quickly. Voila, the encoders are connected to the Teensy. We're going to set this aside now, and we're going to spend some time writing some USB code, and then we'll test it out. To code this, we need to do 2 things. Modify the Teensy's USB stack to pretend to be the programming wing, and then write a sketch that sends the right packets at the right time. With the Teensy Arduino software installed, when you build a sketch, you can select what kind of USB device it presents as. But none of these will result in ETC Nomad recognizing our Teensy as a programming wing. We'll have to add a new one. Find the Teensy code. On a Mac, it's inside your Teensy Arduino app. Right-click and show package contents, and then navigate to Contents, Java, Hardware, Teensy, AVR, Cores, Teensy3. Here we care about 2 files, usbdesk.h and usbdesk.c. usbdesk.h contains a section for each of the USB types that were available in the menu. I'll scroll down to nearly the end and add a section for our new type. I'm calling it USB ETC EOS, although that name doesn't matter, I could call it anything. Now I start filling in values. Most things I copy straight from our previous USB prober data. Vendor ID, product ID, manufacturer name and its length, product name and its length, number of endpoints, number of interfaces. The next few things, which I've started with IFC, are details of our endpoints. Again, the names don't matter. I called them IFC since that's what they seem to be called in the USB interface name, but anything will do. Finally, we tell it that endpoint 1 is transmit and endpoint 2 is receive. That's it for our header file. Let's move on to the C file. This file is long and has multiple sections. We'll have to change things in a few places. We'll start by adding an interface descriptor, which I'll paste in here. Again, this data is all copied from USB prober. I won't go through every field here, but there's a few to draw your attention to. We're starting to use all those IFC values we defined in the header. Note that for the transmit endpoint, we bitwise OR it with OX80, because that corresponds to the OX81 we saw in the prober. These mentions of ETC EOS report desk, we're about to go and define those. In the same file, just after the other HID descriptors, we'll add hours. This is simple. It's a direct copy of the bytes that we saw in USB prober. I didn't bother to work out what all the values mean, because it doesn't matter. As long as we send the same thing as the wing, we're good. We need a few more defines to make the compiler aware of the existence of our new configuration. I'll drop them in and make sure to change the config desk size to leave enough space. And here as well, we add our HID descriptor and config descriptor. Now the USB stack knows about our new configuration. We need to do one more thing to make it available in the menu of Teensy. Going back up to the AVR directory, we need to edit boards.txt. Scrolling down to where the Teensy USB options are defined, I add a pair of lines to describe our new configuration. The top one is a human-readable name, and the bottom one matches the constants that we used in the USB desk files. Finally, let's see if it builds in Teensy. We select our new configuration from the menu and click Validate. Uh-oh, an error. Endpoint transmit only undeclared. Oh, wait, I made a typo. I put transmit. Let's fix that. Now it's giving an error in yield.cpp, where it can't find serial. I've seen this before. With our new USB configuration, there's no serial channel for the Teensy to communicate. Let's go edit yield.cpp and fix that. I'll make it only compile the serial event code if USB serial is present. And now our empty sketch validates. It's time to write the actual code. We'll start with some imports, and a struct holding the encoder data, which I'll instantiate 4 copies of. Also a value for each encoder. I do this because my encoders are a finer resolution than the wings, so I only want to send a USB packet when I've seen at least a certain number of notches. Some more USB stuff. I'm lifting this from some of the other Teensy USB code for the configurations that were already in the menu. You can find this code in the same folder as USB disk. Here, this USB IFC data array is where we'll put our outgoing packet before sending it. And RX packet is where we store incoming packets, which, if you recall, will give us the header for our reply. Init encoder just sets up one of those encoder structs, and we'll call it for each of the encoders during setup. During the loop, we want to read a packet if there's one available. I'll copy in both of these functions later. They're also heavily based on the existing Teensy USB code. We want to update our encval numbers. I'll also paste in this function later. Then, in some code that suggests I haven't discovered loops, we check if the encoder value is above a threshold. And if so, we call this EOS encoder nudge send function and reset the value back to 0. Here I'm adding the USB IFC functions. Don't worry about how they work. Other than replacing the constants with ones we defined earlier, I didn't change them. EOS encoder nudge send is more interesting. This one relies on some of the packets that we reverse engineered. For all of those, bytes 0, 2 and 4 were values 3, 1 and 4 respectively. So we'll set those. Then there's a byte that represents each encoder. It's bytes 5 through 8 as I define in the encoder locations variable. I'll null those out to clear old data. And then for the encoder number passed into this function, I'll set the respective bytes to 1 if it's an increase and 0xFF if it's a decrease. Then the rest of this function just sends the packet. Again, this is copied from the Teensy examples. We check this and it compiles. Let's see what happens when we run it. And now the moment of truth. It's time to connect it up to Nomad and see if it works. I've got Nomad's diagnostics page open on the laptop, and I'll just plug in my Teensy. And we can see board detected type playback master. This is looking promising. If we now look at the numbers at the bottom of the screen, I'll see if I can adjust the pan and tilt of channel 1. Yep, those two encoders seem to be working, and now I'm going to switch page. Remember, this is something that the open source solution can't do. And it now adjusts intensity. Great, a successful demo. What, you guys are bored of just numbers changing on the screen? You want to see it connected to the actual light? Oh, go on then. You have no idea how hard it is to record under these conditions. I can't see a thing. I'm sat point blank range from a spotlight. I've had to turn my camera's exposure right down. Still, it's what you wanted. I've now got the laptop connected up to the moving light. We can pan. And tilt. And if I can squint through the haze to the computer screen, I'll switch page to colour. And now I can select from a nice range of different colours that this light has to offer. So there you have it. Here's how we can control moving lights using a Teensy. If you were to reverse engineer a USB device, what would it be? Let me know in the comments, and I'll see you next time.